Hello and welcome back to Real Analysis. And of course, many thanks to all the nice people that support this channel on Steady or PayPal. In today's part 12, we talk again about the limit superior and the limit inferior. Here please recall, for any sequence of real numbers, this lim_sup and lim_inf always exist. Namely, they are either a real number or the symbol minus or plus infinity. Also, I can tell you, some people write this set as an interval. There we use brackets to say that the symbols minus infinity and infinity are included in the set. Okay, since you already know this, let's look at an example. So here I take the sequence an given as -1 to the power n times n. Hence the sequence starts with -1, then comes 2, then -3, then 4, -5 and so on. Obviously this sequence is not convergent. However, we find a subsequence that is divergent to infinity. Hence the lim_sup has to be infinity. Then in the same way, we find a subsequence that is divergent to minus infinity. Hence the lim_inf has to be minus infinity. So you see, this is a simple example, but it tells us that all the elements in this set are possible values for the limit superior and limit inferior. With this in mind, let's formulate some properties. First, let's discuss what we have for convergent sequences. Here please recall, the lim_sup is the largest accumulation value and the lim_inf the smallest one. Therefore, a sequence is convergent if and only if the lim_sup and the lim_inf are actually the same. And of course, there should be real numbers. This is not hard to see. If the sequence is convergent, lim_sup and lim_inf are actually the limit. On the other hand, if they are the same, there's only one accumulation value, therefore the sequence has to converge to this value. Okay, now we can extend this result and talk about the case when the limit is infinity. So we say the sequence is divergent to infinity. Then lim_sup and lim_inf have to be the same again, but now there should be infinity. Please compare this to the example because there it is different. They are not real numbers, but they are not the same. Okay, another thing I can tell you is that the lim_sup is always the largest accumulation value, so always larger than lim_inf, therefore we can just ignore this part here. This immediately follows if we know that the lim_inf is infinity. Now next, maybe not so surprising, we can do the same for the limit minus infinity. And this holds if and only if the lim_sup is minus infinity. Now all of these things here are easy to show when you know the definitions we discussed in the last video. A little bit more complicated is the next property where we combine two different sequences. Okay, now for sequence an and bn you could ask what is the lim_sup of the sum. So lim_sup an plus bn. In general, this is not equal to the sum of the two limit superiors, but only less or equal. However, please keep in mind, this only makes sense if the right hand side here is well defined. For example, infinity plus minus infinity would be not defined. Now this is the only exception of this inequality. For example, you could have infinity plus 5 and this would be infinity again. Okay, now in the same way, for two sequences you could ask what is about the product. And it turns out it's the same thing. The lim_sup of an times bn is less or equal than the product of the two limit superiors. However, in general this is not correct because we could have different signs for the sequences which would flip the inequality. Therefore, let's formulate and remember this property for non-negative sequences. However, also here we have an exception. For example, 0 times infinity is not defined. This is important to know whenever you calculate with the symbols minus and plus infinity. Okay, I would say proving these two inequalities is a very good exercise for you. Because when you do this, you immediately see that we have a similar inequality for the limit inferior. So it's the same in green here, the only thing that changed is the direction of the inequality. So the lim_inf on the left hand side could get bigger than the right hand side. To see that this is in general really an inequality, let's look at an example. So here we need two sequences of real numbers. I want an to be 1, minus 1, 1, minus 1, and so on. And bn to be 0, 2, 0, 2, and so on. With this information, we can immediately calculate the sum of the two sequences, which is simply the constant sequence with value 1. Hence simply a convergent sequence. Therefore the lim_sup and the lim_inf of the sum are simply 1. And now we know from the properties above that we have inequalities here. Indeed, here in this case they are actually strict. Because here on the right hand side we have 1 plus 2, which is 3, which is strictly greater than 1. And for the lim_inf we have minus 1 plus 0. So also here strictly less than 1. Okay, now of course we can do the same for the product. However, for this we should take non-negative sequences. Therefore, let's formulate this with a new example. So we can take the same sequence for bn, but for an we have to substitute minus 1 with 0. Then the product sequence is just a constant sequence, now with 0 as the value. Of course, then the lim_sup is 0 as well. On the other hand, the lim_sup of an is 1 and the lim_sup of bn is 2. So we have 2 on the right hand side. Therefore also here we see in this example we have the strict inequality. Okay, after all this, the important things you really should remember are the 4 inequalities we have for lim_sup and lim_inf. And when you have time, maybe you also find an example where we have the strict inequality for lim_inf. Later you will see we can use these inequalities a lot in calculations. Okay, I think that's good enough for today, and I hope I see you next time. Bye!